Alright, this lesson we'll talk about the solving linear trig equations as well as solving quadratic trig equations. Really, lesson 6 is the skill we want to focus on, but lesson 5 is a good sort of warm up and helps us get started or get sort of set the table for what we need to do in lesson 6. Now, when you're solving a trig equation, okay, this is the same thing we were doing last unit where we are attempting to find the x, right, that makes the equation true. So just like any other, solving any other equation, you're trying to find the x that makes the equation true, right? So like, here, sine x equals 1. What x makes that true, right? And, at some point during the process here, we are probably going to need an inverse function. And you know that whenever you use an inverse function, you introduce the possibility of not the possibility, the requirement of a second answer. So we're going to want to review how to do that and, look at solving these trig equations. So they sort of start with, they sort of start a little bit light. So let's just go through and remember how these ones work. So sine x equals 1. This is one where I wouldn't expect you to need to use a calculator for something like this, because of course if sine x is equal to 1, we know that there's only one place on the unit circle that sine x is equal to 1, and it's up here, right? This is the only y value of 1 on the entire circle. There is no second place where that occurs. And so we could just say x is equal to pi over 2, right? Because that would correspond with the idea of the max of sine, right? And we know that sine, when you sketch it out, it's only equal to 1, once, like right there at pi over 2, right? So whether you do that with the drawing or whether you do that with the unit circle, it doesn't really matter. But you do need to know that sine x is 1 when x is pi over 2. Now, the second part of the question gives us an interval on which to provide our answer, which is just an important thing to take a note of because, normally it'll ask you between 0 and 2 pi, and for a lot of questions you can kind of ignore that because 0 to 2 pi is one cycle, or sort of like the standard solution space that we're looking in. But we do need to be careful about this and pay attention to it, because depending on the question we're doing, this might have implications, right? So for now, for this one, I know that to get from 0 to 2 pi, sine completes one cycle, and sine only reaches its maximum value once. And so, I only need to give that answer. It's the only answer in that interval that exists. Okay? Now, the next one, where it says cos x equals 0, well, if you think about cos, right, and again, let's do the same thing where we can sort of draw it, and then we'll look at it from this point of view as well. I can see cos is equal to 0, 1, 2 places, or remember cos is the x coordinate, right? So it would be 0 right here at 0, 1. It would also be 0 right here at 0, negative 1. So our answers would be pi over 2 as well as 3 pi over 2, right? And that would correspond roughly with, if you think about dividing this into 4, right? So here's pi over 2, here's pi, and here's 3 pi over 2, and then 2 pi, right? So the two x-intercepts of cos are at pi over 2 and 3 pi over 2. So x equals pi over 2, 3 pi over 2, right? And then that's your answer. Again, those are the only two answers in the interval I was asked, so I know that my answer is complete. I don't need to give additional answers, and I know both of these should be accepted because both of them are in the interval that I was supposed to look in. Again, it's easy enough to check something like this, right? You're just going to, again, you might want to, for purposes of doing this sort of stuff, change your graphics view to count in a number that's more suitable to radians. Like rather than count by 1, 2, 3, 4, 5, and so on. So you just right click, you go to graphics, change your x-axis, and so that you measure the distance in pi over 2s. You can measure them in something else if you want. You can measure them in pi over 6 or whatever, but pi over 2 is usually pretty good. So we can draw cos x. We can notice there are indeed 2 times it is 0, 1 at pi over 2 and 1 at 3 pi over 2, right? And those are our 2 answers, so easy enough to check. Now, next one here says root 2 times sine x take away 1 equals 0. So again, root 2 sine x take away 1 equals 0. Again, to solve something like this, we want to isolate sine, and then we want to inverse sine. Okay, that's sort of the strategy we're going to use. So first thing we're going to do is move that 1 to the other side. Then we're going to move that root 2 to the other side. And once again, I don't really need to use an inverse sine here, because 1 over root 2 is an exact value, and I know the angle that goes with that, right? If you think about this one, I know that at pi over 4, the point is 1 over root 2, 1 over root 2. And since the y value is positive 1 over root 2, I want to keep that as one of my answers. The other time this would happen would be over here at 3 pi over 4. Remember, if you're counting by pi over 4s, it would be 1, 2, 3, 4, 5, 6, 7, and then 8 to get back to normal, right? So 5 pi over 4 would be down there. 7 pi over 4 would be down there. Now, all of these have the same values, right? As 1 over root 2, 1 over root 2, except what's negative and what's positive about them. In this quadrant, both of them are negative, and in this quadrant, only the y is negative. Now again, my question is asking me all the places where sine is 1 over root 2, and sine is the y coordinate. So I'm going to keep this one, and I'm going to keep this one. I am not going to keep this one, and I'm not going to keep that one. They're in the wrong quadrants, right? So my answer would be x is equal to pi over 4 or 3 pi over 4. Again, very easy to check something like this. What we're going to do is we're just going to look at, what we're going to do to check this, we're just going to load up GeoGebra again. We're going to sketch the equation we were just given. Oh shoot, I shouldn't have done that, sorry. I keep forgetting that every time I do this I have to reset that. Alright. Okay, so it was square root 2 times sine x take away 1, right? So that was our equation. Now we were supposed to draw this equation between 0 and 2 pi only. Okay, so we're only looking in that interval, and we're supposed to find all the places where it's equal to 0. So you can see it's equal to 0, right there and right there, more or less right there, right? And the significance of these values is there. So let's posit that one answer is pi over 4 and one answer is 3 pi over 4. And then I'm going to sub these into my function g. Okay? So g of a, 0. G of b, 0. So it solves my equation, right? Remember my equation, I was looking for what value of x makes the whole equation 0. And the answer is pi over 4 or 3 pi over 4. Which you can confirm on this picture. You can also confirm that there are no other answers anywhere else on the in this interval for the graph. Okay, and that's how you could do number 3. Now they do get a little bit more complicated when they don't work with nice exact values, like the next two are not going to, and the last ones, these ones also get harder because they start messing around with the argument. So, I think these exercise 6 are quite a bit more difficult. This exercise 1, 2, and 3 hopefully is not too bad, because all you're doing there is just noticing your exact values, and your unit circle could solve all of these questions. Your unit circle is not going to be able to solve the questions, though, when you get numbers that you don't recognize. Like, for instance, this one, 4 sine x plus 1 is equal to 0. we're going to need to find out when sine x is equal to -1/4, and we don't have a special triangle that has that answer in it. So let's go ahead and do this. This is more of like a full algebra type of question, right? Where we it's a little more involved. So first thing we're going to do is we're going to bring the -1 to the other side. Then we're going to bring the 4 to the other side. And now, in the previous question, we could look at the unit circle. You can't do the unit circle really here because we don't have a point on it that's -1/4. So what we're going to end up having to do is inverse sine of -1/4. Now remember, whenever you inverse sine anything, it's complicated, right? When you inverse sine a negative number, the calculator is going to tell you negative beta. Okay, the calculator is going to tell you negative beta. And you are also to know that the places to look for where sine is negative would be Q3 and Q4. So we're going to take negative beta. Obviously, we're going to change it into positive beta. Then we're going to get pi plus beta, which will be our quadrant 3 answer. And then we're going to get 2 pi minus beta, which is going to be our quadrant 4 answer. Okay, and that's how we're going to approach the rest of this question. So first of all, when we do this, we find that negative beta, which is the thing that the calculator is about to tell us, is equal to what? So let's go ahead and delete this. And we're going to do inverse sine of -1/4. So it comes back with the number 2527, -0.2527. I'm going to keep 4 decimals. 0.2527. Now, that tells me that beta is 0.2527, and that my answers are places where sine is negative, namely Q3 and Q4. So a Q3 would be one of my answers, Q4 would be the other. So in my Q3 answer, okay, so try and remember if I go back to my equation now, I'm going to take this over, and x would be all that's left on the left side because inverse sine took care of it, would be equal to, pi plus beta. So x is equal to pi plus 0.2527, and x is equal to, pi plus that number. So pi plus, absolute value. I get 3.39, I'm just going to have this round to 4, 3943. Sorry, 3.3943. Now, in quadrant 4, x would be all that's left on the left side, but on the right side, I would have 2 pi minus beta. So x is equal to 2 pi minus 0.2527, and x would therefore be equal to 2 pi minus a, or plus a, I guess, since a is a negative number, the way it's written here, 6.0305. Okay, now if what we did is right, then what we should be able to do is, plug them into the equation. So let's make the equation. So 4 sine x plus 1. Okay, so that's the equation. And if I sub in these numbers, f of b, I get 0, and f of c, I also get 0. Okay, once again, you can kind of look at the picture. You can type function, and then it says which function, where do you want it to start, where do you want it to end. I want to draw function f between 0 and 2 pi. Right, so there's the space I'm supposed to be looking to find my answer. Right, I'm only looking on the interval 0 to 2 pi. And I see there are 2 answers. One answer is over here at 0.3943, exactly where we said it was. The other answer is over here at 6.0305, exactly where we said it was. Okay, so that's how you would approach these questions. And you can leave your answer like this, or you can say x equals 3.3943, comma 6.0305, and that's all there is to it. Okay. This one, the exercise 5, is more of the same. the exact same question. It's just using secant, which is a little bit different. So let's go through it. So for secant, we're going to say secant of x plus 5 is equal to 0. Therefore, secant of x equals negative 5. And therefore, 1 over cos x is equal to 1 over negative 5, right? Which is what... sorry. 1 over cos is secant, apologies, is equal to negative 5. And then what we can do is we can take the reciprocal of both sides. So reciprocal of both sides. And then we get cos x is equal to negative 1/5. And that's what the that's what we get here. So, so from here to here, I'm just using an identity, but I'm not doing anything to the other side, right? I'm just altering what the left side looks like. But to get from here to here, I'm changing both sides. I'm doing the reciprocal of both sides, right? To change from there to there. Okay, so yeah, I mean, okay. So anyway, so we get to this, and now what we have to do is inverse cos. Inverse cos this side, and inverse cos this side. Now remember, when you inverse cos a negative number, your calculator is going to tell you pi minus beta. You are going to look for answers in Q2 and Q3 because you're looking for places where cos is negative. Now the Q2 answer is pi minus beta, so you can just accept what the calculator tells you is the answer in Q2. To get the answer in Q3, though, we got to do a little bit of maneuvering, right, to figure out beta and then place it in the right quadrant. So let's go ahead and split the answer into two. And we're going to have a Q2 answer and a Q3 answer. And in the Q2 answer, x is equal to pi minus beta. And the calculator is let's get what the calculator tells me. So I'm going to do the inverse cos. Let's delete everything here first. Okay, so inverse cos of negative 1/5 is 1.7722. And that is our first answer. This is what's good about cos, right? It can tell you the answer in quadrant 2 directly. I do need to do a bit of work, though, to get into quadrant 3, because I need to do pi plus beta in order to get there. So I need to find beta first. So pi minus beta equals 1.7722. So pi minus 1.7722 equals beta, and then I can figure that out. So beta equals pi minus a, which is 1.3694. And that's beta. Okay, so then in my quadrant 3 answer, I have pi plus beta, and therefore in my quadrant 3 answer, I would have pi plus that number, so pi plus beta, which is 4.511. Now, those are the two places where secant will be equal to negative 5, and our equation will be equal to 0. Again, let's go ahead and draw it. So we're going to draw it first. So secant x plus 5. So secant x plus 5 is that. I only want to draw it for one period. So once again, I'll type function f comma 0 comma 2 pi. That will draw the function for one period only, which is what this one's asking me to do. And I see that there are two solutions. There's a solution down here and a solution right there. And those are the exact same solutions we came up with. Another way that you could do this, of course, is you could just sub in our numbers, f of a and f of b, and both of them give you 0. Which tells us that we're right. Again, it says express your answer to two decimals, so we could cut it 1.77 and 4.51. But anyway, whatever. Okay. Now, so all of these up until now have more or less been what we already knew. We did this in Unit 5. We did the inverse and all the problems that causes, and get your two answers, find your beta. What does it all mean? Now, here's where we take this to a bit of the next level, okay? Where, what about when what's inside cos is not, is not just x, but here it's 2x, right? So here we have cos 2x equals negative 1/2. I'm not going to work with theta. Whatever. You can work with theta. It doesn't matter. I'm just going to work with x. Now, cos 2x equals negative 1/2. So, all right. The difference between what we're about to do and what we were just doing is only the following. Okay? Now, you already know that when you take the inverse of a negative, you're going to be looking for a quadrant 3, a quadrant 2, and a quadrant 3 answer. In the last question, okay, what I did was I took the inverse, and then I said x was equal to and x was equal to, okay, and then we got our answers. Here, the only thing that's different is that it's not x that's equal to this, but rather 2x. Okay, because 2x is the argument. And the argument, okay, will be equal to pi minus beta in Q2. In Q3, the argument will be equal to pi plus beta. So the only thing to note that's different about this than the one before is that the argument, is 2x here instead of x. Now that seems like, okay, well that doesn't sound too hard. It does change something else about the question too, though, and this is why I'm saying we have to be on our toes. So let's keep going anyway. We'll get the answers and we'll go from there. So in quadrant 2, I'm expecting the answer to be 2x to be pi minus beta. In quadrant 3, it'll be 2x will be pi plus beta. Okay, and then I'll find that out and I'll divide it by 2, and that will tell me x. So once again, I'm going to inverse cos negative 1/2. Now, negative 1/2 is a exact value that you should recognize, right? I mean, when this one, in a pi over 6, pi over 3 triangle, it's 1 to root 3 to 2, and we know that if pi over 3 is the angle you're looking from, then this is the adjacent, this is the hypotenuse, and so we know the reference angle is pi over 3. Okay, and so if you inverse cos this, what you're going to get is pi minus pi over 3, which is your quadrant 2, answer. You're going to get 2 pi over 3, right? That's going to be what your answer is. Now, suppose we didn't recognize that, we could just use the calculator to do it, right? I mean, you should recognize when it's an exact value, but if you don't, you can try this too. You can inverse cos negative 1/2 and get that number. Now again, you might not recognize that number is 2 pi over 3, and that's why you got to be a bit careful here, and knowing your exact values is important, right? So anyway, I mean, we should recognize that 2 pi over 3 is the answer, and beta would be pi over 3. Okay, so in this quadrant, in quadrant 2, 2x would be 2 pi over 3, which is the quadrant 2 answer. In quadrant 3, 2x would be 4 pi over 3, which is the quadrant 3 answer. Remember, in quadrant 2, pi take away beta would be pi take away pi over 3, which would be 2 pi over 3. In quadrant 3, pi plus beta would be pi plus pi over 3, which would be 4 pi over 3, which is how I'm getting those two things. Okay? Alright, so far so good. I divide both sides by 2, and I get that x is equal to 2 pi over 6, which is x is equal to pi over 3, is one solution. And then x is equal to 4 pi over 6, x not pi, x is equal to 2 pi over 3. And those are our answers. Now, this person hasn't made a mistake and has collected 2 right answers, but is not going to get full marks for this question. Why not? You see, pardon me, something to be aware of when you're solving trig equations is to be aware of the solution space. And the solution space in all the questions we've done so far has just meant we look for 2 answers, because you look for 2 answers because there's only ever 2 answers in that solution space, right? Yeah, there is an except. There are three solutions to the equation sine x equals 0, because there's 0, pi, and 2 pi, but that's a bit of an anomaly. Let's just leave that aside. Here, what's the problem here? The problem here is that when you go back and look at the questions we did before, okay, 0 to 2 pi is 1 period, right? 0 to 2 pi is 1 period. 0 to 2 pi on all these questions, 0 to 2 pi is 1 period. Okay, what about in this question? Well, remember, the period of a function is 2 pi over k, and here k is 2. So 2 pi over 2 means the period is just pi, which means we're not actually looking at 1 period, we're looking at 2 periods when we're doing this question. So how do you know, that I need to look for more answers or not? In every question you do, find the period, and every time you think you have the answer, try adding a period or subtracting a period to every answer you get. Ask yourself, does the one that I get when I add a period or subtract a period land in the solution space? If it does, keep it. If it doesn't, your answer's done. For example, here, if I did pi over 3, if I add a period, okay, so let's say I'm writing out my answers. I know my answers pi over 3 and 2 pi over 3, that those are two of my answers. Now, if I subtract a period, from each, I get negative pi over 3 and negative 2 pi over 3. Now, these are too low, because remember, I'm starting at 0. So I don't need to subtract a period in this one. I might need to subtract a period in other ones, by the way, which is why I'm bringing this up. How about adding a period? What about if I add a period, plus a period, plus a period? I'm going to get 4 pi over 3 and 5 pi over 3. Now, if I add another period onto those, which there's no reason I should stop right now, right? I got to keep going until it doesn't work anymore. Now I get 7 pi over 3, which is too big. 7 pi over 3 is going too far. So I don't need to keep these ones, and I don't need to keep anything higher. So those are my solutions. Pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. Those are all the answers. Why is this difficult? Is because not only do you have to do all the inverse stuff that, hopefully is becoming more, comfortable for you, but it is complicated. And but not only that, you need to make sure at the end of the day that the answers you collect include answers from nearby periods if necessary. And the only way to know that is to pay attention to the solution space. So, another thing that can help us, of course, with this is, we can draw. I mean, and that's useful because it will alert us to the idea that there's more answers. So, for example, here, let's draw it. So, cos 2x equals negative 1/2. Sorry. I'm just losing my mind. Cos 2x is what we're drawing, and then we're looking for when it's equal to negative 1/2, right? Which is there. Now here's the issue. If I say, let's draw this function f between 0 and 2 pi, notice that it does not go through one cycle, it goes through two. And therefore, you're not just collecting the answers here and here, which is what our calculator told us. We're collecting those answers, and then we're also sending them to the nearby period, another cycle. That's still part of our answer. So you see our answers, right? We had an answer at 2 pi over 3. We had an answer at pi over 3. We had an answer at 4 pi over 3. And we had an answer at 5 pi over 3. Now again, if you gave these ones with decimals, if you did it with decimals, I think that's probably fine. I think you should know that, when it's an exact value, you should use the exact value because it actually makes it easier rather than trying to remember all the decimals. But whatever. If you ended up giving the answer 1.047, 2.09, 4.18, 5.236, that's also right. The only reason that wouldn't be right is if the question said exact values. If it said exact values, you'd have to say pi over 3, right? And again, if you ever want to sort of check if your answer is a logical fraction of pi, take your answer. So x of d, for example, this number 5.236. I don't recognize this number. I don't know that this number is a fraction of pi. But what I can do is I can go a divided by pi, okay, and then I can go fraction text b, and now I see, oh, it is a fraction of pi. It's 5 pi over 3, right? And so if you take your decimal, as long as there's enough decimals in it, and divide by pi, sometimes you can tell the exact value even if you didn't get it. You know what I mean? Even if you sort of get it at the end, that's fine as well. Okay, let's see how this would change with b, and then I'm going to stop this video and I'll start a new one for the quadratics. So this one works to our advantage, because where the other one we had 2 periods in the answer, this one it's going to be the opposite, right? So we have cos x over 2 equals 1/2, and the period of this is 2 pi over k. In ours, k is 1/2, so the period is 4 pi. So what are we drawing here is we're drawing half a period. We're not even drawing a full period, right? We're only drawing half of it, which means we are likely going to cut one of the answers at the end. We're not going to have to add new ones. We're probably going to have to remove one, right? Because probably only one of the answers will show up in half a period. In any case, let's go through and answer it. So cos x over 2 is equal to 1/2. Once again, I know that if you inverse cos 1/2, the answer you're going to get is pi over 3. That's beta. I'm inverse cosing a positive number, right? When I inverse cos a positive number, it tells me beta. I'm expecting 2 answers, a quadrant 1 answer and a quadrant 4 answer. 2 pi minus beta, which is 5 pi over 3, okay? Which would be 2 pi take away pi over 3. 6 pi over 3 take away one of them, okay? So those are my 2 answers. Now once again, I split it up into quadrant 1 and quadrant 4, and I don't say x equals, I say x over 2 equals, right? Because I need to deal with the fact that it's over 2. In my quadrant 4 answer, I have x over 2 equals 5 pi over 3. Now again, to solve it, I'd simply bring the 2 to the other side. And here. Okay, and so my solution is 2 pi over 3 and 10 pi over 3. Except, right? Except 10 pi over 3 is too big. And I'm going to reject that one, because if you think about it, I'm only looking for answers between 0 and 6 pi over 3, which is 2 pi. And 10 pi over 3 is all the way over here, right, which is too big. Obviously, if I add a period or subtract a period, it's going to be going too far. So, you should think about whether you need to do that. But of course, in this situation, if I add a period of 4 pi and my solution space is only 2 pi wide, it obviously makes sense that I'm not going to get another answer in my solution space. So this is not going to lead to new answers. This is not going to lead to new answers. This answer needs to be rejected. So the only answer I'm going to keep is this one, right? The 2 pi over 3. So in a way, when your argument is being divided by a number and your function's being stretched, that works to your advantage because it lengthens the period and likely reduces the number of answers you're going to keep. When the number is a compression that's compressing your function, you're going to end up with answers you might not think to look for. And you got to be careful about this by adding and subtracting periods until you fill the solution space with all the answers that it asked for. Okay, so let's just demonstrate this one with a video, with an image, and then we'll stop here. So it says cos of x over 2 is what we're supposed to draw, and we want to know when it's equal to 1/2. Okay, and this is the picture that we get. Now once again, you can see that it's equal to 1/2 in many places, but if we're only looking at this function f, so function f between 0 and 2 pi again, we're only looking at half a period. And indeed, there's only one answer to this in the section we're looking for, and that is right here at 2.0944. Now, once again, say I had to find the exact value, and I didn't recognize that number, right? Then I can take that number, x of a, right? So if you do x bracket a, it basically says what's the x coordinate of a, right? So there's the x of a. If I divide that number by pi, and then I go fraction text b, it tells me 2 over 3. So 2 pi over 3 is the answer I'm looking for, right? And that's what we said before. So even if you're struggling with the exact values, you can still sort of work around it using this technique, right? So get the x value of the point you need, divide it by pi, and then find out what that is as a fraction, and that will help you find the exact value. Okay, so that's it for solving equations. So basically, there are two things to know. Okay, the first thing to know is what we've been doing last unit. You need to, do the inverse, and then get your solutions. If you inverse cos a negative, you inverse sine a negative, like what does it mean, and how do I get the answers, whatever. The second thing to be aware of is if you have something in the argument, like a multiplication, for example, or an addition, or something inside the argument, remember that the whole argument has to come with you, and the argument is what is equal to pi minus beta, or pi plus beta. Okay, so even if we had a question that was like cos 2x minus a half, right? Minus pi over 2, let's say. What I would do here when I inverse cos is just bring the whole thing with me. Pi plus beta or whatever, right? Like this whole thing comes with you, and then the whole thing comes with you over here. Equals pi minus beta, whatever. Let's say I was doing that, right? So that's all, the only two things to remember. Sorry, let me add one last thing. Because we are messing around with the period, oftentimes the questions, if the questions don't change where they're looking, it might change what you have to answer. So for instance, if this one actually said the period of this function between 0 and 4 pi, which is what maybe it should have said, then we would have to keep both answers. Since it only says 0 to 2 pi, we're not actually completing a period here, and therefore one of our answers is not kept. In the previous question, it actually wanted us to find all the answers within 2 periods, which means both the answers we got are good, but we also need to find the answer in the neighboring period by adding a period to each answer to get another answer. And you could see that if they needed us to go further, we could keep doing this as many times as we needed until we got far enough that we could stop, right? And that would depend on what the question was asking. Okay, so that is lesson 4.5 on solving trig equations.